Hello students, today I am going to cover syllabus on BSc Fifth Semester Paper 1 Real Analysis, in which Section 1 or Unit 1 Riemann Integration. I am Dr. Krishna B. Chavreddy, Government Postgraduate College, Narmad. This is the syllabus of Karnataka University BSc Fifth Semester. So today in this session, I will cover upper and Riemann integral and R integral. So we justify these definitions with problems. So to define the Riemann integral of f, we only need a few more things in mind. Each partition P has a maximum subinterval length not P. Each partition P and the evaluation set E determines the number of S of f, right? Simple calculation. So if we took a collection of partitions P1, P2 and so on, associated evaluation sets E1, E2, etc., we would construct a sequence of real numbers SP1, E1, SP2, E2 and so on, Sp and En. Let us assume the norm of partition Pn smaller all the time. That is, limit of norm Pn as n approaches to infinity is 0. We could then ask if the sequence of numbers converges to something, if the sequence we construct above converges to the same number, no matter what sequence of partitions whose norm goes to 0, and associated evaluation sets we choose, the value of this limit is independent of the choices above. This defines the Riemann integral of f on closed interval AB. Let us define upper and lower Riemann integral along with the R integral. First, we can see that here. Let us suppose f is a bounded function defined on a closed bounded interval AB. Define the upper and lower Riemann integrals respectively as the infimum of upper sums is called the upper integral and is denoted by infimum of UP of f equal to upper integral f of x dx, and the supremum of lower sums LP of is called the lower integral and is denoted by Sup of LP of equal to lower integral of x. So if upper integral equal to lower integral, the function f is R integral, and the Riemann integral of f over the interval AB is denoted by integral of f of x over a to b. That is, the upper Riemann integral equal to lower Riemann integral that equal to the integral. This holds, then we call it as a Riemann integral. So let us say some notice on this concepts. The upper and lower Riemann sums depend on the particular choices chosen, and the upper and lower integrals are independent of partitions. However, this definition is very difficult for practical applications, since we need to find supremum and infimum over any partitions. Historically, the idea of Riemann integral was developed using area approximation as an approximation. So the summing nature of the Riemann sum was denoted by 16th century letter capital S, which resembled an elongated or stretched letter S. This looked like what we call that integral sign. Hence, the common notation for the Riemann integral of on closed interval AB, and this value exists is integral over E f of x dx. We usually want to remember what the independent variable of f is also. And we want to remind ourselves that this value is obtained as we let the norm of partitions goes to 0. Since for a function f, the name we give to the independent variable is a matter of personal choice. We see that the choice of the variable name we use in the symbol integral of f of t, where t is the variable here. That is, variable is their personal choice. That is what we said it here. So now let us see the examples to justify the above definitions. Show that the constant function is R integrable over AB, and also find the value of the integral. First, let us divide the interval AB by division P equal to A x naught, x1, etc. xn equal to B. Then each of the subinterval xr minus 1, xr, we have a supremum and infimum respectively k there. So now we can substitute those infimum and supremum in upper and lower Riemann sums to find that is the k into p minus a there. So then we can substitute these in the upper integral and lower integral. As we know that definition of the upper integral is limitation of the upper sums as n approaches to infinity. Then respectively, that is the lower integral is also same as we got it upper integral. So that then obviously this is what this constant function is always r integrable over ab. So value of this integral is k to b minus a. And also that function x square is Riemann integral on the closed interval 0, 1. If so, find the value of Riemann integral. Do the same for the interval -1 to 1 then. We can exactly follow the same procedure as we have done in previous problem. So definitely this function x square is Riemann integral. By finding this, proving this, it is Riemann integral over Riemann. Find the upper and lower Riemann sums and upper and lower Riemann integral. And ultimately, this is f of x equal to x square is r integral over 0, 1. So value of this integral is 1 by 3. That. So do the interval for -1 to 1. Definitely we can do that also. In third problem, the density function f is defined by f of x is 1, where f is 1 at every rational number x there, and f is 0 at every irrational number. Then show that it is not upper integrable. Definitely, since it is a discontinuous function, so that always it is here, it is bounded, but it is not a continuous, not a hard integrable then. Same because supremum of f here 1 and infimum of f it is 0. So definitely that is UPF and LPF getting different values. So that ultimately upper and lower Riemann integral also different. So that obviously it is not arguable. So that we have referred to those references. So that thank you.